Today we're going to talk about force, and we're going to introduce the concept of force and the things we're going to be doing today. We're going to start off with things that are really obvious and so easy that it will at first seem kind of confusing. We're going to go through a series of activities where it's going to be real easy at first, then it's going to be pretty easy, and then it will be a little bit challenging, the last one. But it's all going to represent the same basic idea. But there's a few things we need to know before we start doing the activities. And one is, what is this thing that we call force? What is force? What is it? Well, here's what in physics, what we mean by a force. Here's my coffee mug. No more coffee in it. And let's zoom out. Okay. Let's see if we can get that in focus. Okay, and so I'm going to apply a force to this coffee mug. Are you ready? All right, so I'm going to apply a force to it. So here we go. Here we go. Wow. Okay. Or, now, so this is what we call I'm pulling on it, right? I'm pulling on the coffee mug, and I'm making the coffee mug move. Okay? I can put a string on it. Do the same thing. Here's a string. String the coffee mug. I can pull on it. So that's a pulling force. Okay? Or I can do this. Whoa. Okay, I told you this was going to be easy. Force. 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 Ah. Okay. So, a force is a push or a pull, and it can change the way an object is moving. So that's pretty basic, right? A force is a push or a pull. It's a push or pull that can move an object around, or change the motion of an object, however you want to put that. Let me zoom in so people can read it. All right. I'm going to be zooming in and out a lot with this. Okay. Now, what do you notice about force, though? What kind of quantity is a force? In order to describe a force, what do I need to know about the force? I mean, what's different about this force? Okay, I'll zoom out again. It's going to be annoying. Ooh, look at this force. Okay, I'm pushing on it. I'm pushing on it. I'm pushing on it all the way to the edge of the table. All right, what about this force? What's different about those two forces? The direction. So what kind of quantity do we call it if it has a direction? Yeah. Force is a vector quantity. I can push on it this direction, this direction, this direction. So force is a vector quantity. So we can add that on here And maybe I'll just write bigger on the paper so you can read it without me zooming in out. Force is a vector. Okay? So that is, it has a magnitude and a direction. And we're gonna identify its magnitude and direction. We're going to put it in polar coordinates. Now, how do we measure the magnitude of a force? Well, let's see. What if you want to know how much force of gravity is on you? What do you do to measure your force of gravity? Well, I get up in the morning and I'm hoping that I've lost some weight, so I stand on a
mountain.
A mountain. I would like to throw you off a mountain. No, this is, you stand on a bathroom scale. Okay? And actually, I guess if you were at the very, very top of a mountain, you would weigh ever so slightly less than you do at sea level. Not enough less that you would even notice it. We'll talk about that when we talk about Newton's law of gravity. But what's different ways of measuring a force? Well, we have pounds, right? Pounds. You can measure a force using pounds. We don't use pounds to measure force, though in this class, we are going to use this unit of measure. Dum, dum, dum. The Newton. The Newton. No, we're not going to use the apple. We're going to use the Newton. Now, it so happens that this toy foam rubber apple, when you hold it up, the gravity pulls down on it with 1 Newton of force. Or if you hold it in your hand like this, you'll feel 1 Newton of force pushing down on your hand. It weighs 1 Newton. Weight is a kind of force. We'll talk about that more later. So a Newton is not very much. Newton is a very small amount of force. It's not nearly as big as a pound. A pound is about 4.5 times bigger than a Newton. Okay? It's named after Sir Isaac Newton. Okay, to honor him and the amazing discoveries he made. Isaac Newton was one of the greatest minds in the history of the human race. He was kind of a jerk, Newton was. Not somebody I would want to party with. But he was nevertheless an amazing human being who did amazing things that we remember to this day because he changed the world we live in. So, but anyway, so what I'd like to do, I'm going to throw this around. Here, who could catch? Who's paying attention? Who can catch? Okay, ready? You did? Oh my gosh. Okay. Huh?
That's a me?
Yeah.
Oh. Well, I tried to catch it.
Yeah, I'm sorry. Just pass it. I'd like everybody to hold it, get a sense of what a Newton of force is. Now, so if I were to draw a force, I would draw it as a vector. Like if this is my coffee mug right here, looking down on my coffee mug, I might push it this way. So it would have a certain number of newtons. That would be its magnitude. And of course, we could measure its angle. And so it would be in polar coordinates. Or I could take my coffee mug and I could pull on it. So same thing. Push and a pull does the same thing. So they have different magnitudes and directions and so on. Those are forces. And they can pull things, move them around. But do they always move things around? Well, yeah, be careful with that. That's my pride and joy, that Newton apple. Okay, I'm going to take my coffee mug and I'm going to push on it like this. Okay, you guys pay attention. Stephen. All right. So look at this. I'm going to do this, and this one says, Okay, I'm having a battle here. A force battle. I'm going to crush this. All right. Notice that the forces can cancel each other out, right? If I add this vector plus this vector, if I add two vectors that are in opposite direction, they tend to cancel each other out. Yes? Does that make sense? So there isn't, if I push on the coffee mug like this from both sides, the force, there are not zero forces on the coffee mug. If I let go, it's going to go like that, or if I do this, it's going to, get pushed that way. But the forces can add up to zero. They can cancel each other out. And when an object is not changing the way it's moving, or if an object is at rest and is staying at rest, when an object has no acceleration, we say that that object is in equilibrium. Equilibrium. If an object is in equilibrium, let me go ahead and zoom in. What does that mean? For our purposes, like equilibrium has different meanings in different, like in chemistry, they have equilibrium and so on. But why don't you give that to me, because it's distracting people. Thank you. It means the object is not changing its motion. Another way of saying is the object is not accelerating. Okay? So that's what we mean by equilibrium. An object is at rest, and it's staying at rest. Or if it's in motion, it's staying in motion. Like if you're drinking, if I am drinking this, coffee, I got some coffee and I put it on my table on a train. Let's say I'm having some coffee on a train. And the train is just moving at constant velocity down the track. The coffee mug is in equilibrium, even though it's moving compared to somebody outside the train. But in its own reference frame, it's at rest. Another way of saying it is that an object is in equilibrium if it is at rest in its own reference frame. Okay. So what we're going to do is we're going to do a series of activities for objects that are in equilibrium, and we're going to learn something about the forces that are acting on that object. Now the object doesn't have to be a coffee mug. It can be something very light and small, which I have here somewhere. Okay. Before we do the activities, I need to show you this. These are spring scales. This is how we measure how many newtons a force has. Now, I can take this coffee mug and I can pull on it, and I can measure the pulling force using a scale. So here it is, and I can put a spring scale on it. And you can't, the string is too long. Kind of a klutz when it comes to real objects. So I can pull on this, and I can measure how much I'm pulling on it with the spring scale. Not very much. Okay. So now I can't push with it though. Spring scales can only measure pulls. I mean, what happens if I try to push on this string? Okay, I'm going to push. It just doesn't work. Another way of saying is that you can't push with a rope. Where I'm from, that was an expression. Can't push with a rope, but you can pull. All right. So when you're pulling on something, you are measuring the pulling force. You can do that with this spring scale. And here's the spring scale, and I'll show you how to use these things here in a second, how to measure the force. Come on, you can do it. There we go. Now notice that there are two scales on this particular spring scale. There's newtons and there's dynes. I have another one where there's newtons and grams. Never mind the grams, we're going to use newtons. Now the first, is everybody watching? Because people got the wrong answer last period because they weren't paying attention. I know this goes on and on, but listen. You need to zero your spring scale. If you lay your spring scale down and just kind of get it ready to go, and it looks like that, you're going to be off by 1 Newton. Ignore the dynes. We do not dyne in this class. Okay? We use newtons to measure force. And so you want to adjust this and make sure that the very center of this tab is at 0. And that looks pretty good right there. And then you can measure the force to the nearest 1/10 of a Newton. Now I'm going to pull on this and hold it, and I want you to tell me how many newtons of force I'm pulling on this spring scale. What is that? 6.5? I'd say a little tiny bit more. What? 6.6? I'd say 6.6 because the center of the tab is a little bit beyond. Now, if you said 6.5 or 6.7, that's pretty good. If you said 6.1, that would be wrong. 6.9 is wrong. And 6.6 was pretty close. The 6.5 is pretty close, and that's what we want. We want to be, that last digit needs to be within 1 of what you're measuring. See? Now there. What is this one? 8 point? What? No, 9 point? Yeah, 9.1. Okay. So if you said 9.0, I'm not going to argue with you. If you said 9.2, I go, it's a little bit much, but okay. If you say 9.4, I'm going to, no, that's wrong. You see what I mean about measuring? Getting that last digit is a kind of a guess, but there is information there. Now, if I did this, and I said, oh, okay, that's 10.67943962 newtons. That's horse manure. Okay, those last few digits. Okay, you can only measure the nearest 1/10 of a Newton using the spring scale. So we can measure the magnitude, and then we can use protractors and so on to measure direction of forces. So here's what we're going to do. Now, we're going to take, I'm going to give you some strings with loops in them. And we're going to do activity 1. Okay, now, we're going to take a loop of string. Oh, sorry. we're going to take a loop of string and we're going to pull on it. Yep. Here's the hook, and then here's the spring scale. Here's your handle. You're going to pull on it this way. And we're going to call this F1. And then you're going to pull on it in the opposite direction with another spring scale. We're going to call this F2. Now what I'm going to do is I'm going to give you several F1s. And I want you to measure F2. Now this is going to seem so easy that at first it's going to seem kind of a big stupid waste of time. But it's not. It's one of the most profound ideas in all of physics. These are forces. They're vectors. So in order to describe a vector, I need to describe a magnitude and a direction. So let's define direction. Let's say this is the positive x direction. This is the y direction. Now we're not really using the y direction yet, but we will. I'm going to go 5.0 newtons, 10.0 newtons, 15.0 newtons. And what angle is this? 0 degrees, 0 degrees, 0 degrees. And what I'm going to ask you to do is give me the magnitude and direction, magnitude and direction, magnitude and direction of F2. I want you to really measure it. Now you might think you know what the answer should be, and that's okay. You've got a hypothesis based on previous experience. That's fine, but I want you to measure it. Now to get accurate results, make sure that your spring scales, both of them, you're going to use two of them, start at 0. One group got these really wacky answers, and it's because they didn't zero their spring scales. And I want you to give me this in polar coordinates. Okay, and then when you do it, I'm going to turn this into more work than it should be. For each one of these, I want you to go what is F1 plus F2? Now what do you have to do to add vectors together? Okay, you have to change them into rectangular coordinates. So I want you to put these into rectangular coordinates before you add them together. And it's really easy to do that on this one. Okay, so I want you to do this in two places. I want you to do it on your whiteboards, and I want you to do it in your notebooks. Okay, I'm going to pause the video now. So I want you, and then we'll hand out the materials and do the experiment. Okay, so pause the video now. So here's the results from one of the groups for activity 1. And I really like the way they laid out F1 plus F2, and they showed their work and everything. So F1 was 5 newtons at 0 degrees. So I'm just going to draw it. 5 newtons at 0 degrees. And then we added to it, F2 was measured to be 5 newtons at 180 degrees. Now it would have been nice to have it to the nearest tenth of a newton, but that's cool. So here's F1 plus F2. Now notice that 0 degrees means nothing in the y direction, it's all in the positive x direction. 180 degrees means nothing in the y direction, it's all in the negative x direction. Does that make sense? I mean, you can use cosine and sine if you want. But, so you have this force plus this force equals 0. So when you add the two forces together, you get 0 force. So then we had the loop like this. I'll go ahead and draw. You had a loop like this, and you pulled on it with this spring scale, pulled on it like this with this spring scale, but now it's with 10 newtons to the right, and then 10 newtons, and then they measure 10 newtons to the left. So you're getting the same force. Are all of you getting about the same force? Right? If you're pulling with 10 newtons to the right, you'll also pull with 10 newtons to the left. So when you add this vector F1 plus this vector F2, you get 0. And with 15 newtons, did you get 15 newtons? Some of you, I asked you to measure the nearest tenth of a newton, and you might have been a little tiny bit off, right? Maybe you measured 15.0 and 14.8, something like that. That's not bad. When you add them up, you won't get exactly 0, but you'll get something that's really, really tiny. In reality, though, if your measuring tools were perfect, you would get 0 when you added the two vectors together. So you take from polar coordinates to rectangular coordinates, you add your rectangular coordinates together, and you get 0, 0, 0. And then you can use Pythagorean theorem and inverse tangent. Undefined 0. Undefined 0 is your magnitude and direct. Well, it's just 0. What direction is a 0 vector? It doesn't have a direction. That's undefined. Okay? Now you all use your data, but I like the way this was laid out. The only thing I'd like to see is to the nearest tenth of a newton. You could have measured a little more precisely. Does this make sense to everybody? Any questions? Okay, we're now going to move on to the next activity. Now we're going to do basically the same thing we just did in activity 1, but we're going to do it with 3 forces. So here's what I do. I've got this string, and it's got a loop on this end, a loop in the middle, and a loop over here. And we're going to take this loop in the middle, and can somebody bring me 3? I need 3 spring scales. Can you bring me 3 spring scales? Perfect. Thank you. You're going to need 3 spring scales, and you might have to share them among the groups. So anyway, but now we're going to have we're going to call this one F1. I can barely fit this on the camera. So one of them from the middle, that's going to be your F1, and then you're going to have F2 and F3 pulling the other way. Put this in here. So I don't know if you can, so you're going to have it laid out like this. So this one's going to pull this way, and these two are going to pull in the opposite direction. I've got 2 strings. They're fairly long. You have to keep them parallel. So that's how you're going to set up your spring scales. And I'll try and draw a picture of it here. Here's kind of the knot in the middle, and here's your loop in the middle. So here's your loop in the middle. And you're going to hook up the spring scale like this. Well, hold on. You're going to have a string like this, and then you'll have the spring scale hooked up to a loop. I don't think that's focused very well. Let me focus that again. So you'll hook up the spring scale like this. And this will be your F1. And then you have the string that comes into twos like this. And one will be a little bit longer than the other. And you'll hook this up to a spring scale. And this one up to a spring scale. And you're going to keep these both to the left. And this is going to be F2. And this is going to be F3. Now, what I'm going to do for this one, we're only going to do one set because this is going to be a little take a little bit of time. I'm going to say F1 is going to be equal to 10 newtons at 0 degrees. F2 is going to be 3 newtons at 180 degrees. So someone's going to have to hold it so it's at the 3. And then someone's going to have to measure F3. But F3 is still going to be at 180 degrees. So I want you to set this up, measure this, then put them in rectangular coordinates over here, add them together, and let's see what you get. Does that make sense to everybody? What I want you to do. Now, you can make a prediction of what you think this should be, and that's awesome. But I want you to measure it and see what it actually turns out. Any questions? Okay, I'm going to pause the video like this, do the work, show this both in your notebook and in the whiteboard. Okay, go. Okay, for activity 2, this is what one group got. Let me activity 2. Okay, so we said that F1 was 10 newtons at 0 degrees, and F2 was given to be 3 newtons at 180 degrees. Now, I hope you actually measured it. I went around and looked at all your whiteboards, and you all got 7 newtons at 180 degrees. Was it actually 7? Yes. Yeah. I mean, it was really, really close. This is true. Now, a lot of you probably thought, oh, it's 7 newtons. Why do I even need to do this? But here's what I want you to see. The universe makes sense. Okay? There's a pattern here. It's very obvious and very simple. But it makes sense. And it's very profound. So, 10 newtons at 0 degrees. Well, that's 10 newtons cosine 0, 10 newtons sine 0. You get 10 newtons, 0 newtons. One thing I like the way you did this, group 3. I like the way you showed the sine and cosine. You don't really need to do that. Most of you didn't do that, and you don't really need to. But I like the fact that you did. 3 newtons at 180 is 3 times cosine of 180 is -1. That's -3 newtons. 3 sine 180 is, sine 180 is 0. And same thing for here. So when you add them up, you get 0. So that string that you're pulling on with 3 different forces is not moving. The string is in equilibrium. And when you add up all the forces that are acting on that string, you get 0. Okay? So, if you have, here's, one of the forces like this, and then you on a loop, and then you had another force like this, and then you had another string, had a force like this. This was 7 newtons, make it a little bigger. This was 3 newtons, and this was 10 newtons. Now the universe works in such a way that if I put 8 newtons right here, what am I going to get right here? I'm going to get 2 newtons. It's got to add up to that. Because when I add all 3 force vectors together, what am I going to get? If it's in equilibrium. I gotta get 0. This is a big deal. Now we're going to move on to activity 3, which is the hardest one. Okay, let's do activity 3, and I'm not going to bring all the equipment up here. I think you know what to do with the equipment now. But you are going to need a ruler and a protractor, and there are rulers and protractors on the table. Wait until I am finished with instructions. Thank you. Gosh, Stephen Sanders. All right.
I've been immortalized.
You've been immortalized. Okay, so here's we're going to make this the x-axis, and this is the y-axis. And then here's what I want you to do. I want the knot that's in the middle is going to go right here. And I'll tell you what we'll do. We'll the string. Well, we'll put the knot, and here's the loop in the middle. And you'll put the spring scale right here. And this will be F1. And F1, I want you to make it, let's see, I want you to make this 6 newtons at 0 degrees. Now use a protractor and a rulers to make these 90 degrees apart, right? X and Y axis, 90 degrees apart. And this is a string attached to it. And then there's a loop in the string here. And then you'll pull up on this. And this will be F2 that you'll measure with the spring scale. This is all horizontal on your table. And I want you to make this to be 8 newtons at 90 degrees. Now, if you pull up like this and up like this, keep this knot that ties all these loops together at the very center, in the origin. Otherwise, your results are going to be bad. But there's going to be a string that comes off like this with a loop like that. Hook the spring scale up here. And this will be F3. Now I want you to measure its magnitude. And then what you need to do with your dry erase marker is draw a little dashed line along the string, or right where this force is, put a little dot and then use a meter stick or something to draw a line. So you'll measure the magnitude of the force with your spring scale. And then, well, this is 180, and then you can use your protractor to measure this angle. So 180 plus this, that will be the angle of it. And then I want you to do this. F1 plus F2 plus F3. We're going to add up all these forces. Now you can't add them up in polar coordinates. You have to add them up in rectangular coordinates. So you're going to need to change this to rectangular, and the hard one is after you measure its magnitude and direction, change it to rectangular coordinates. Like this is your x direction, this is your y, so it's going to have a negative x, it's going to have a negative y components. And I want you to add them up. Now, what do you think they're going to equal? We'll see. We'll see. If you say they're going to add up to 0, that's a good hypothesis. But let's find out. Does everybody understand what I want you to do? Okay, make it so. Put it on your whiteboard and in your notebook. So, from activity 3, this is what this group did. They pulled F1, F2 like this. They measured F3 and they got an angle for it. They measured 10 newtons. That's right on, people. That's what it should be. Did you get 10? Or something really close to 10? 9 is pretty close to 10. Should be 9 point something. And then the angle they got was 235. 235. Now, if your measuring was perfect, I think it'd be 233. So but that's really, really close. And so when you take F3 that we measured and we break it up, using cosine and sine, the way they showed right here, you get this value and this value. So 6 plus 0 plus negative 5.7, well, you get 0.3, which is pretty close to being 0. And then here you have 10 times the sine of 235. Well, you have 0 plus 8 plus negative 8. You'll get 0. I mean, actually, to the tolerance of our measuring, the uncertainty of our measurement, this is pretty much indistinguishable from 0. So if you add, watch this, I'm going to do this, F1 plus F2, and then here's F3. That gets you back to where you started. F1 plus F2 plus F3 gets us to 0. Okay, so the essential question was this. Okay, don't put your stuff away yet. You will get out of here on time. I'm almost done. Well, what's true about the forces acting on an object that is in equilibrium? They always add up to 0. But you have to add them as vectors. I want you to discuss that in the summary for your essential question. That is your homework, is just to do that. Are there any questions? I love you all.